Every chip fab on Earth stores drums of it in climate-controlled rooms, treated with the same care as a rare pharmaceutical. It is a light-sensitive chemical so finicky that a single contaminant measured in parts per billion ruins the entire batch. Without it, a lithography machine costing hundreds of millions of dollars projects onto nothing, the same way a camera lens without film captures no image. In 2023, Japan's Ministry of Economy, Trade and Industry named that chemical on a restricted export list targeting 42 Chinese firms, and in doing so, handed those same firms the most precise industrial roadmap they had ever received. The chemical is photoresist. Insiders call it the goo. It is the light-sensitive layer spun onto a silicon wafer before each lithography step. Light passes through a patterned mask. The goo records the geometry. Chemistry strips away the exposed portions, and what remains is the circuit. No goo, no pattern. No pattern, no chip, regardless of how advanced the machine printing it is. Japan targeted the goo rather than the machines, and that choice was sharper than most export controls ever get. It was also, I think, a more consequential mistake. What follows is the story of how a regulatory document became a research and development agenda. Why the outcome challenges every assumption embedded in technology, export controls written over the last decade, and what the goo tells us about who actually benefits when a choke point is named out loud. Japan's Ministry of Economy, Trade and Industry placed 12 core chip materials under tightened export rules. The list included argon fluoride immersion photoresist and extreme ultraviolet photoresist, the two most advanced categories of the goo used in modern chip production. 42 specific Chinese entities were named. This was not a broad embargo. It was surgical, targeting chemistry rather than equipment or intellectual property, cutting further upstream than prior Western controls had reached. The logic was sound. A lithography machine is a complex tool, but its operating principles are documented in academic literature and patent filings. Photoresist formulations are harder. The performance of a given resist depends on polymer architecture, photoactive compound ratios, solvent blends, and processing conditions that interact in ways competitors cannot simply reverse engineer from a product specification. Japan's chemical firms had spent decades refining these formulations. Restricting them was a genuine choke point move. A 300mm wafer gets coated in a photoresist layer roughly 50 to 100 nanometers thick, thinner than a soap bubble, and that layer must be chemically uniform to within a fraction of a nanometer across the entire surface. The margin for error is narrower than the wavelength of visible light. Japan's leading chemical producers had learned to hit that margin reliably, at scale, across millions of wafers. That knowledge is not written down in a single document. It lives in process engineers, in equipment calibrations, in institutional memory built over 2 decades. So the surface story reads like a clean win for export control policy. Here's where it lands differently. At the time Japan issued those controls, China's domestic photoresist production covered roughly 10% of its own demand. That figure comes from industry analyst estimates and Chinese government-linked industry reports, so treat it as an approximation, not an audited number. But even as an approximation, it is striking. 10% self-sufficiency on a single point of failure input is roughly what a city achieves when it grows a tenth of its own food during normal times and calls the situation manageable, until someone else controls the roads. The dependency was not a surprise to anyone paying attention. Chinese semiconductor policy documents had flagged photoresist as a critical vulnerability for years before the METI controls arrived. The flagging had produced awareness. It had not produced supply. Japanese chemical firms supplied the bulk of what China's fabs were running, a structural dependency built over 2 decades of global supply chains optimized entirely for efficiency rather than resilience. The METI list did something those earlier policy documents had never managed. It made the vulnerability legible with specificity. 12 materials, named, ranked implicitly by the order in which they would constrain production. A sanctions list, targeting 12 specific inputs, functions the way a hospital's critical drug shortage list functions for a contract pharmaceutical manufacturer. It tells you exactly what to produce, who needs it, and with what urgency. Japan issued that list. China read it. China's official response included a stated target of roughly 40% photoresist self-sufficiency by 2026, up from that 10% baseline. That figure is a government projection, not an independently verified engineering milestone, and the distinction matters enormously. State investment and subsidies have flowed to domestic photoresist developers with the explicit mandate to close the gap. The funding is documented and real. The technical results at advanced nodes are not yet independently confirmed. Here I want to be direct about the gap between a production target and a qualified process. Extreme ultraviolet photoresist must respond to 13.5 nanometer wavelength light, formulating a resist that absorbs at that wavelength, patterns sharply, strips cleanly without residue, and does all of this at production speed across millions of wafers, is among the most demanding materials engineering problems in manufacturing today. The global leaders in extreme ultraviolet photoresist have spent decades and enormous capital on iterative refinement, protected by deep patent portfolios and the kind of tacit knowledge that cannot be photocopied. Chinese domestic producers have demonstrated real competence at older argon fluoride photoresist grades. Extreme ultraviolet grade material is a qualitatively different problem. Getting from argon fluoride to extreme ultraviolet is not like climbing a taller version of the same hill. It is closer to having mastered road cycling and then being asked to qualify for open water swimming. Related disciplines, different physics, entirely different failure modes. 3 counter-arguments deserve honest weight before anyone declares this story resolved. First, the 40% target is a volume goal, not a quality certification. Filling 40% of demand with domestic material means nothing to a chipmaker if that material fails yield qualification. Volume and certification are different finish lines, and only certification matters to a fab running production. Second, Chinese photoresist developers have published performance claims, but independent verification from non-Chinese fabs or third-party analytical laboratories has not been widely reported. In a domain where contamination measured in parts per trillion can destroy a batch, self-reported purity figures carry limited weight. Third, extreme ultraviolet photoresist sensitivity and line edge roughness operate near the physical limits of what polymer chemistry can currently achieve. These are not engineering problems that scale linearly with investment. There are fundamental materials, science constraints that cannot be subsidized away on a 2-year timeline. The honest synthesis: the direction is clearly set, the funding is genuinely committed, the target is ambitious, and the hardest part of the technical problem has not been publicly cleared. Anyone telling you China solved photoresist because a ministry announced a target is skipping the 3 points above. What I find most striking, and what I think gets underreported, is the pattern this fits into. The sequence of restriction-producing dependency mapping, which then drives a forced domestic buildout, has now repeated across multiple technology categories in less than a decade. Memory, logic chips, electronic design automation software, and now specialty chemistry. Each round of controls has produced a more detailed Chinese understanding of exactly where its supply chain is exposed. The controls are, inadvertently, a recurring audit of Chinese industrial weakness, conducted by the restricting countries and delivered to Beijing without charge. Japan's Ministry of Economy, Trade and Industry made a technically sophisticated call and a strategically self-limiting one at the same time. Targeting chemistry rather than machines showed a genuine understanding of where the real choke points sit. But a choke point only holds if the other side cannot build around it, and a document listing 12 named materials is not a permanent barrier. It is a renovation schedule. The restriction was correct about what mattered. It was wrong about what that information would accomplish once China had it. If China reaches even a fraction of its photoresist target at qualifying purity, the leverage Japan holds over Chinese chip production contracts in meaningful ways. That leverage was real in 2023. Its shelf life is now being actively measured in Chinese laboratory budgets. The goo Japan tried to control is now the goo China is spending the next 2 years learning to make it scale. Whether they get there at extreme ultraviolet purity, on schedule, at defect densities a leading fab will certify, I do not know. And neither does anyone who is not standing inside a Chinese materials facility right now. The direction of travel is clear. The finishing line is not. The most dangerous thing about a control list is not what it stops. It is what it teaches. If China hits 40% photoresist self-sufficiency by 2026, Even at older process nodes, does Japan's entire rationale for these controls begin to unravel? And what threshold would that need to reach before the leverage disappears entirely? Drop your read in the comments. If this kind of granular industrial strategy breakdown is what you come here for, subscribe and turn on notifications. A new one lands every week.